Hello guys, I am Puneet and today we will solve the mass transfer questions from GATE 2017 paper which was organized by IIT Roorkee. But before we go further in the individually talk about the questions, I would like to share something. So here is the mass distribution in mass transfer from GATE 2011 to 2020. So this distribution is topic wise. Let I have distributed like mass transfer 1 and mass transfer 2. And if I will conclude the whole mass distribution, then distillation, absorption, and liquid extraction are the most important topic that you will see. And there will always be one question at least from this topic, from these three topics. Okay, so I mean, if you are preparing and you are in hurry, then you should never leave these three topics because one thing is clear that mass transfer always contributes more than 10 marks. Okay, in the last 10 years, that is from 2011 to 2020. Okay, and if you want to go in more detail, like how you should prepare the mass transfer for GATE, then there is a link on the top right corner. You can go through that video, and it will give you an idea like this is the way to prepare for mass transfer if you have limited time, and even if you don't have limited time, you have to smartly prepare for the mass transfer or any subject for GATE. Now moving forward to the mass distribution in 2017, so there were 7 questions and 3 questions were of 1 mark and 4 questions were of 2 marks, so which as a whole were 11 marks. So out of 100 marks of GATE, 11 marks were contributed only from the mass transfer. So as a whole, like it's a very important subject. So without any ado, let's get started. This is our first question and which is from liquid extraction. Okay, and they are asking about the plate point. Like there are some situations that you will observe when you reach to the plate point in a liquid extraction. But we have to understand first, like what is this plate point? On that basis, we can finally, like what is the right option for this one? If you look at the plate point, so we know we have a ternary system that is a composition of A, B, and C. There are 3 components. It's a ternary system. Now we want to separate them as AC system and BC system. And A and B are partially miscible to each other. So you will see that there is a curve that is from that started from the D and it will go all the way to this one to G. And area under this curve, this whole area will contribute to, like if you have any composition, the composition of A, B, C should be under this curve. Only then you can separate it as a raffinate and extract. And there is one specific point where you will see like this point, P point. This is the point where you will not be able to differentiate between the extract and the raffinate phase. So this is our raffinate phase and the rest of the curve is of extract phase. So at some point where they will meet, that point is known as plate point, where you will not be able to separate the extract phase from the raffinate phase. They will look exactly same. So what it means is, now if you will come back to the question, you will see, now you know plate point is the point where the extract and the raffinate phase will look exactly same, which means there should be no density difference. If there will be density difference, they will definitely separate from each other, okay, on the basis of gravitational force. And if it is interfacial tension, even then they will separate like we have the oil with respect to water. But there is no such thing because the composition will be exactly same. So there is the interfacial tension should also be equal to 0, density difference should also be 0, and if they are at the same composition, so the last option is definitely correct. So all these 3 options are correct, which define the last option, PQR is the right answer for this question. Okay, so you should know what is plate point, and then it's like nothing. It's very easy question. Now moving forward to the second question, which is from distillation. It's a 1 mark question again. So there they have this, they mentioned that they're talking about the Murphy efficiency actually. Okay, so there is this composition given to us that we will discuss later. But first we'll learn like what is this Murphy efficiency. Okay, so you know in distillation we have 3 types of efficiency. One is the overall efficiency, second is the Murphy efficiency, and third one is the point efficiency. Now, what we understand from overall efficiency, so it's like you have to tell what is the efficiency of the whole distillation column as a complete one single unit. You have to tell this is the efficiency of the whole system. But when we go to Murphy efficiency, which means we are talking about the tray efficiency, now we are specific in that complete column. Okay, now we are inside the distillation column and we are looking at individual plates individual levels and try to see what is the efficiency of every individual level. That is decided by the Murphy efficiency. Finally comes the point efficiency. In the point efficiency, we are talking about the individual points on one single plate. So far, like first we said the complete efficiency of the system of the whole distillation column. Then we talk about this is the efficiency of the plate. Now we are going to talk about what is the efficiency on that plate on specific point. The efficiency can be different also. It is decided on the basis like how big the diameter of the column. But all I'm saying is the difference between, here we are talking about the efficiency difference, like what is the overall efficiency, Murphy efficiency, and the point efficiency. So they have asked about us, like we have to calculate the Murphy efficiency here. Now if you look at back the question, so they mentioned that the composition, the vapor entering the tray, this is our distillation column, okay, and they are saying that the vapors are rising up slowly up to the top. So we have now a tray n, and then we have a tray n plus 1. So whatever the vapors that will leave from n plus 1 will enter at n, okay, and from n there will be new vapors that will leave and which will be yn. So the vapors that just about to enter are yn plus 1, the vapors that are leaving are yn. So on that basis, if you will go to the Murphy efficiency, that is yn minus yn plus 1 upon yn star, that is the equilibrium efficiency minus how much what is the composition of the vapors that are about to enter the plate. Okay, so if you will solve it, we will find that it is 120%. So this is the Murphy efficiency, that is the efficiency of one specific plate in the distillation column. And you should know that Murphy efficiency is the only efficiency which can go more than 100% also. So you will see, like if you will go back to and look at all the questions, all the GATE questions, you will find like 1 or 2 times they have specifically asked, can Murphy efficiency go 100%? And then answer is yes, it can go more than 100% also. Now coming to the third question, and this is again from mass transfer 1, actually interphase mass transfer. Okay, so here they have mentioned that there is a very specific point. You should be careful with this one. The steady state mass transfer is happening, and they mentioned that we have a liquid system, we have a gas system. Now they came in contact, and because of which some of the gas component is now diffusing into the liquid, and they have reached the steady state mass transfer. Now they are asking, like if this relation is equal to 0, so what we can understand about the mass transfer resistance. So let's understand the situation. So situation is that we have the liquid phase, we have the vapor phase, they come in contact, okay, and there is one component diffusing continuously from the gaseous phase into the liquid phase, and the system has reached to steady state. Steady state means the things are not changing with time, but the component is still diffusing from the gaseous phase to liquid phase, which means the mass transfer in the gas phase will be equal to mass transfer in the liquid phase. We can go to this way. So here we have the steady state condition, and we have balanced like at what rate the component is diffusing from the gas phase into the liquid phase. And if we will solve it, they have mentioned that this value is equal to 0, which means automatically this value is also 0. And we can write this one as 1 upon KL divided by 1 by kg, which is equal to again 0. Now to be this value equal to 0, 1 upon KL has to be 0. And KL is the mass transfer coefficient, and 1 upon KL is the resistance of the mass transfer. Okay, which means, so 1 upon KL means there is 1 upon KL is equal to 0 means that there is no resistance in the liquid phase, because 1 upon KL is 0. KL is 0. 1 upon KL means resistance is 0. So which means that the option B is correct, which mentioned that you will not feel any resistance when the component will enter into the liquid and it has to diffuse through the liquid. Okay, there will be no resistance. Before I go further to 2 marks questions, I would like to update you guys that we are also on the platform of Facebook and Instagram. You can follow us. The link will be in the description box. And for the Instagram, you can just directly scan the barcode and you can directly will be on the Instagram with us. Now, moving forward to the fourth question, which is again from distillation. Okay, and this question is of 2 marks question. Now, in this question, they have asked like there is a 3 component system. We have methane, ethane, propane, A, B, C, methane, ethane, propane, and they have given the vapor composition. I mean, the mole fraction in the vapor phase they have already provided, and the relative volatility also. Relative volatility means with respect to something. Here they have said that N propane is the baseline, and with respect to that, methane has this relative volatility, ethane has 4 relative volatility with respect to propane. Now they have asked like if we know the vapor composition, can you find out the liquid composition of propane? Okay, that's what they're asking. So for that, we will use few equations here. So if you will look, so where I have just labeled them as like methane as A, ethane as B, and propane as C for like equation purpose. And these are the compositions provided us in the vapor phase. Okay, so now we are going to use 3 equations here: the Raoult's law, relative volatility, and third one is that all the mole fraction summation is always equal to 1. So we will use all 3 equations one by one and try to see can we calculate the liquid composition of N propane in the system. Moving forward, these are the 3 equations given to us. We will do one thing. We will use this Raoult's law and substitute this value in the third equation. So after you will put it, you will reach to this equation. You will have this equation. Now we know that the relative volatility is with respect to propane, and we know that relative volatility is the ratio of vapor pressure of a component with respect to vapor pressure of second component, and we already know the value. So better we write that equation in that manner. So what I did is multiplied the whole equation with the PCV, the vapor composition of propane. So if you write it down, so you will reach to these values, these 3 values, and these are the relative volatility. So the equation will be like this. So once you will solve this equation, like now we have already taken out total pressure as outside, and we have vapor pressure of propane on the right side. If you will solve, finally you will end up with this equation, because we already know YA, YB, YC, alpha A, alpha B, and alpha C. You can easily solve and reach to this equation. Now, still we are not nearby to like what is the composition in the liquid phase. So we will again use the Raoult's law. As you can see it here, we already know the YI, or we can say YC, for because the propane case we know YC. PT we don't know, but we don't have to worry because PC, this PC will have this PC will have the relation that we have calculated here. So no problem at all. So you just put the values and you can calculate the X value. So if we will use all these, so if we will use that equation, the Raoult's law equation, and put the PC we have already calculated back as 0.682 PT. So we'll just put that value. PT will cancel out with PT. So you will left with is XC is equal to 0.6 divided by this specific value, and you will end up with 0.879. This is the mole fraction of propane in the liquid phase. So we started with the vapor phase. We know the relative volatility in the vapor phase, and we end up with the mole fraction of propane in the liquid phase. So if you have to calculate for other components also, you can do the same manner and calculate the mole fraction of methane and ethane also in the liquid phase. Now before I go further, like still 3 questions left. So I would like to give just like this is just a guidelines, a recommendation if you would like to, if you are preparing for GATE, like what type of books you should prepare. So you will see all these books in the market, and it's like GATE Tutor is a very popular book, but this time it's not popular. M. Subbu is doing fine in the market. It's a really good book with all the questions starting from 1989 to 2018. So you will have all the questions, all the solved questions. I don't find any errors so far in this book. So it's a very good book. And if you like, if you are looking for that book, the links will be in the description box. You can go through it. Now moving forward to the 5th question, which is a relation, a dimensionless relation is provided to us, that the Sherwood number correlation for the laminar flow is provided to you. The Sherwood number is equal to 0.664, Reynolds number is to 0.5, Schmidt number is to 1/3. Now they're asking Like, can you express the relation for JD, that is a Chilton-Coleman JD factor? You have to calculate the relation for that one on the basis of this one. So you can solve this question only when you are aware about the dimensionless number and the analogies. That is the Reynolds analogy and Chilton-Coleman analogy, all those analogies I'm talking about. So you should be aware about these things, only then you can solve this question. So I think that you know, so let's solve this question. So we know Stanton number is the ratio of the Sherwood number divided by Reynolds number into Schmidt number. And Chilton-Coleman is a relation as JD is equal to NST, Stanton number, into Schmidt number raised to the power 2 by 3. So we have to calculate NST. Once you put this value here, we can solve it. And this is given to us. This relation is already given to us. So all we have to do is divide the whole equation, divide the left and right hand side with the, because we have the Sherwood number, now we need the Reynolds and the Schmidt number. So divide the whole equation with Reynolds and Schmidt number. So you will have the relation like this. Okay, now put this value into the JD equation. So once you will put it back, you will end up with this relation 0.664 upon Reynolds number raised to the power Reynolds number raised to the power 0.5. So that's the relation for the Chilton-Coleman analogy JD factor. Moving forward to the next question, which is from the absorption. It is again of 2 marks question. This question is little, interesting. I mean, it's not just about, the formulas. This time you have to be aware, like you should have the visualization how the things are happening in the question. Only then you can solve this question. So it's a very interesting question. Like they have mentioned, there is a counter current system. I will explain it in the more diagram form. We have this absorption tower available to us. This is our absorption tower, and the exit level has 1, and I have put this exit level as 2 stage. Okay, 1 and 2 stage, although it's a continuous system. Okay, so what exactly they have given? They mentioned that the pure steam will enter from the bottom, and there is a liquid system is there where the solute has the composition in the form of mole ratio, not mole fraction, it's mole ratio as 0.25. Okay, pure steam, I mean, that means the composition is automatically 0. They have now mentioned that this liquid, the liquid that has entered the system, it will exit after it comes in contact with the steam. It will end up with like 0.05 composition. Okay, now they are asking what was the flow rate of the pure steam. I mean, to reach to this composition, how much amount of steam is required in the column. Now, according to the diagram, they have already mentioned the equilibrium diagram. They have mentioned like for the 0.25 composition, this 0.25 is this composition. Now, as the liquid is about to enter, okay, and the steam is about to leave, it means they have to be in equilibrium, right? So the steam that will leave and the liquid that is about to enter, they has to be in equilibrium, which means that the steam will have 0.15 according to the equilibrium diagram. So this is equal to 0.15. So now you know y0 is equal to 0, you know y1 is equal to 0.15. Similarly, you know x0 and you know x2. So all the compositions are known to you, and you also know what is the flow rate of the solvent, not solution, flow rate of the solvent that is going to enter from the top. Now you have to find what is the flow rate of the pure steam. So I will do the material balance of solute here. This is what exactly happens. So steam will enter from the bottom, the liquid will enter from the top. Sorry, this is the liquid from the top, this is the steam from the bottom, and similarly after like they comes in contact and reach the equilibrium, this is the composition. Now once you will solve, because now you know you have to calculate the value of R, you have to calculate the value of the flow rate of steam. You already know the value of S. So once you will solve this equation, you will end up that R is equal to 4 mole per second. So all you have to aware how to read the equilibrium curve. You should know when the steam that is or any other gaseous form that is about to leave the column from the top is always in equilibrium with the liquid that is about to enter the column. If you have that one, you just go to the curve, directly find out the composition, you're good to go. Okay. Now this is the last question from GATE 2017, mass transfer last question. Although this is from adsorption, but I don't find anything like you should know, you should have a proper concepts about adsorption. You don't need anything, like they haven't even asked about the formula, they didn't even ask about any definition or anything. It's just a basic question with the unit. Okay, you just have to know how to use the units here. So how exactly I used here? If you look at the question, they mentioned that we have a 1 liter of system, okay, and out of which 100 milligram per liter phenol is there in that 1 liter. So 1 liter 100 milligram phenol is available to us, and you are using 5 gram of adsorbent to remove some amount of phenol from that batch system. Okay, and at any point of time the equilibrium composition is given to you as 1.3 C. Q star is equal to 1.3 C. What is the value of Q? Q means milligram of phenol adsorbed by the per gram of adsorbent. What I'm saying is how much a milligram of phenol has been adsorbed by the adsorbent. Okay, and this is equal to 1.3 C. See, they have also mentioned this is a concentration in the liquid. Now this is a batch system. Okay, so let's say at any point of time, if out of this 100 milligram, X gram is left in the system. At any point of time, X milligram is still left in the X milligram of phenol is still left in the solution. Then 100 minus X has been adsorbed, right? Which means, like, if you will solve, so X will be equal to 13.34 milligram per liter. That's the amount that can be adsorbed by 5 gram of adsorbent. Sorry, 13.34 is the amount that is left in the system. So rest of the 87 or 86 point something amount has been already adsorbed by the adsorbent. Okay, so that's how you should solve the question. So it's just about the units. You just have to write down, like, just expand it a little bit, and you just go through this is 100 minus X, then this is X, because we already know phenol is of 100 milligram, right? And we have here 1 liter, we have still here 1 liter. Why? Because for 100 milligram the whole liter will not change much. So I have considered as this is an assumption, like 1 liter will still remain as 1 liter, because out of 100 milligram is like nothing. Okay, so it will not make a major change in the whole system. So that's how we solve the last question of the paper. That's it. So thank you very much, guys. So, and all the best for your preparation. We will very soon upload some new solutions of the GATE paper. Jai Hind.